I've turned on the power supply. I've got 18 volts, 1.27 amps. That's about 20 watts. It's surging through this inductive choke. We've got the secondary coil and the primary coil oscillating with a 3.6 nanofarad capacitor. The wirelessly, we got 724.3 kilohertz coming wireless through the air, and there's a wire from the top of the coil coming down like that, and we put an aluminum plate. It lights it up everywhere. Now, just for fun, we can take that yellow wire from the base of the secondary coil here and attach it to an aluminum plate across the table like this, and then nothing else is connected, only the blue wires from the feedback coil are going into the driver. And as we turn the voltage up, we can see light come on. 5 volts, 10 volts. Look at that, 18 volts, 20 volts. You know, there's several different ways to make an oscillating circuit in terms of basic electromagnetic physics. One way is to have a primary coil made of thick wire like this, about 10 turns. Inside of it you put another secondary coil about 750 turns. And when you feed the current, DC current, into this primary coil through these green wires, this will make an oscillation of the secondary coil through these white wires. And the secondary coil will oscillate like in a lens sense, Lenz's law. And if you take one of these white wires like that and feed that reverse signal back into the gate of a transistor or a MOSFET, that'll make the whole circuit oscillate. That's called like a Slayer exciter. It's very exciting. However, the disadvantage of this is any power from the secondary coil comes back to that wire in resonance into the transistor or MOSFET, and it can damage it by its extreme power. So this is one way to do it, but not really the ideal way. Now, there's also a second way to make an oscillating circuit called 0-volt switching. You have a DC power supply here. It goes through 50 turns of wire here called an inductive choke just to control the flow. And you have a 16-turn primary, around 1,000 turn secondary coil. Now, the DC power comes in right to the middle of that primary coil. You can either go up 8 turns or down 8 turns. If it goes up 8 turns, it goes into this MOSFET here, the red wire. If it goes down 8 turns, it goes into this MOSFET here. It's an alternative circuit. And there's some diodes have been added between the yellow gate of that MOSFET here and the red parts, so that when one's on, the other's off, vice versa. This is well known for 0-volt switching. Don't worry about what all that is. Now, the way this works is the primary coil has a capacitor put in parallel with it. And if there's no secondary coil, you can just put in any value, like 500 nanofarad, 1 microfarad. It'll change the LC frequency. But if you have a secondary coil here, then you have to adjust this carefully, typically 1 to 20 nanofarads, so the frequency of the primary and the capacitor match the natural frequency of the secondary coil. Then you get resonance, and you get a very nice energy transfer to very high voltages and frequencies, like very high kilohertz, kilovolts. Now, let's just see how this circuit works. I've turned on the power supply. I've got 18 volts, 1.27 amps. That's about 20 watts. It's surging through this inductive choke. We've got the secondary coil and the primary coil oscillating with a 3.6 nanofarad capacitor. The wirelessly, we got 724.3 kilohertz coming wireless through the air, and there's a wire from the top of the coil coming down like that, and we put an aluminum plate. It lights it up everywhere. We got a wire from the bottom of the coil coming right out to another aluminum plate. It lights up everywhere. So we really get quite a lot of useful wireless power out of this system, and it's highly recommended. And the advantage of this is the output of the secondary coil, these wires, which I just showed you, 2 wires, they never come back into the electronics. So the circuit stays very cool. It goes to very high power. So this is complicated, but works very well. 2 MOSFETs, 0-volt switching, based on the LC circuit of the primary coil and a capacitor in resonance with the secondary coil. Next, I was going to try to use transistors in this system rather than MOSFETs, but that won't work directly because these fast diodes, which turn the MOSFETs on or off, drop them to something less than the turn-on voltage, which is like 4 volts, maybe at a 0 volt, 1 volt, and the transistors are still on in that region. So these fast diodes won't turn off the transistors in a flip fashion. For that reason, we have to use a feedback coil instead, as we'll see now. We're going to look at a flyback driver circuit with 2 transistors, not 2 MOSFETs, primary coil, feedback, and secondary coil, that will create wireless energy from the secondary coil, but only under very precise conditions. So we come over here, we've got 7 volts, 0.6 amps, and look, you see the wireless energy is coming out quite nicely. We can go up to 10 volts, 1.2 amps. The wireless energy is just coming out quite brightly. So that's very cool. Now the question is, how does that work? It turns out that you have to put a capacitor in parallel with either the primary or secondary coils, and here's a 5 nanofarad capacitor that has to be very precise. And now we still have the same flyback driver circuit with 2 transistors, a primary, a feedback, and a secondary, but I'm putting the capacitor in parallel with that little coil and not the big one. And there it is at 7 nanofarads. Can't read it. And now we put the thing up here and test it. We again get wireless energy, but with only capacitor parallel with the top one. Let's go to 10 volts and see what happens. And we get a very strong light. Now in a previous experiment we did almost the same thing, but we used 2 MOSFETs there and there instead of 2 transistors, which we use here. Now for the MOSFETs, you don't use a feedback coil to get feedback. You put these fast diodes in a cable between the drain of one MOSFET and the gate of the other one. So if voltage comes in, saying that gate to turn it on, it gets drained off and goes down the hole of the MOSFET that's turned on, so the other MOSFET never gets turned on in an alternate fashion. Let's just see how it works. You have 2 MOSFETs here, a flyback driver, 1 MOSFET, 2 MOSFETs, 2 fast diodes, one's connected to the gate of that one, and it comes down here and drains out when that one's on, so that MOSFET's off. Or if that MOSFET's on, you reciprocally have a second fast diode over here, which will turn the other one off. So they're turned off reciprocally, primary coil, secondary coil. You have a capacitor here which tunes the whole thing. Typically, they say 0.68 microfarad, which is 680 nanofarad, but I found that 3.6 nanofarad is okay. Anywhere in the range 1 to 5, a much wider range than for these transistors. So let's just turn the thing on and see how it works. There we get 20 volts, look at that. And it's coming on quite nicely at 20 volts. So the general thing to learn here is these MOSFETs, you can do exactly the same thing with MOSFETs or transistors, but the MOSFETs will take a different, wider range of capacitance here, like 1 to 5, whereas these transistors take a very narrow range of capacitance in these coils, like exactly 5 or exactly 7. Both work, but they work by slightly different principles. Now what I've tried to do next was to make a flyback driver circuit for resonant power using only 1 transistor. And here's how it works. We have DC power over here, a voltage divider 220 and 22. The main power goes to a primary coil through the transistor back to ground. A low voltage down here of the voltage divider goes to a feedback coil into the base. So we get a lens interaction between the primary and the feedback up and down, so that it turns it on and off at a high frequency. And that's what you're seeing here. This one's turning on and off at 1300 kilohertz. And we're putting about 8 volts through it from a DC power supply. The current's coming to the primary here, going back down the red wire to ground. Off the voltage divider we have a little thing coming up to the feedback coil through a little 2.5 nanofarad capacitor coming back into the base of the transistor. You can change to no capacitor, 2.5 is about the most you can put here, any sort of little value of nanofarad. Now the trouble is, no matter what you put there, it doesn't light up any wireless power over here. So it doesn't activate the lens interaction from this big secondary coil. In several previous videos, I've shown you how to make wireless energy using two MOSFETs that flip back and forth, or using two transistors that flip back and forth. In the last video, I tried one transistor flipping back and forth with a feedback coil like this one at the top of a primary and secondary. It didn't work. However, with further research, now we have found that we can have this feedback system and use one MOSFET instead of a transistor, and it works to make wireless energy so long as we have a driver to control it. Let's just see how this works. We have one power supply here, DC, that puts energy through the primary coil. It'll go down through the MOSFET here. It's really a MOSFET, although it's an old transistor on the sheet, and it goes back into ground. Now that won't turn on until we get some voltage from the feedback coil. There's a voltage divider here, 220 and 27 ohms, and it'll run stuff into the feedback coil, and when the voltage gets high enough here, it will turn on the MOSFET. So here's your major power supply here, and we have a voltage divider here, two resistors, 220 and 27, and that little wire here that goes up to the blue labeled wire into the top of the 50 turn feedback coil, then back down again to this blue wire, and we put that into the driver here. We can turn on the MOSFET. Now what we can do in the first experiment, just to get started, we can take this yellow wire from the base of this tall 1000 turn secondary coil, and we can put that into the gate of the MOSFET driver, which makes that MOSFET over here work, and we'll put a multimeter on it so we can read the frequency. Now let's turn the voltage up here to like 20 volts. And we have 25 watts, 1 amp. We have a nice 307 kilohertz frequency, and over here it's producing a lot of wireless power. No surprises there. And when we do this, right now we've got a 10 nanofarad capacitor in parallel with the primary. That'll help to control the frequency. Just join to the 6-turn primary coil, and we studied how much capacitor you have to have. Secondary coil feedback, 12 volts, 8 ohms I did it at. No capacitor, we get about 0.4 amps. We get a bright light, 306, just what we saw. Up to about 10 nanofarads, we keep the same thing. I've got a 10 on there now. If we get to about 100 or 220, the light gets very weak, capacitor gets too big. Now that's just our control experiment. Now instead of a yellow wire, let's put this blue wire from the feedback coil and see what happens. That's what we really want to do. Okay, now we're getting feedback from this feedback coil out of that voltage divider over here through the feedback coil, back down the blue wire into the gate of the MOSFET. There's no physical contact now between that huge secondary coil and the rest of the MOSFET driver circuit. So let's turn the voltage up. Go to 15, for example. If you look at it, this thing turns on at about 15 volts. There we go. It turned on at about 16 volts. And at that point, we can come over here and see how much wireless energy is being made sympathetically. There's quite a reasonable amount of wireless power coming out of it. Let's go up to 20 volts. 20 volts, 21 watts, 1 amp. Come over here now, get a nice bright light. Very satisfactory, okay? So what we've done here, we've used a single MOSFET to make wireless power using oscillation between this feedback coil and the primary coil, and the secondary coil has no physical contact with the oscillating system. This is a commercial driver, and that's a commercial MOSFET. I also looked at different capacitor sizes. For the feedback coil, 13 volts, 8 ohms. And small capacitors again work well. Very bright light, up to about 5 nanofarads. I've got 10 on there now. And if we get to very high values like 47 or 100, it shuts off. So this is a very successful test. We've managed to make wireless energy from a single MOSFET and a commercial driver by using a 6-turn primary coil, a 50-turn feedback coil, and a 1,000-turn secondary coil, and there's no physical contact whatsoever between the secondary coil and the rest of the system. Now, just for fun, we can take that yellow wire from the base of the secondary coil here and attach it to an aluminum plate across the table like this, and then nothing else is connected, only the blue wires from the feedback coil are going into the driver. As we turn the voltage up, we can see light come on. 5 volts, 10 volts. Look at that, 18 volts, 20 volts, 1 amp. So we're lighting up a fluorescent light at a distance from a wire taken from the bottom of that coil rather than the top. So this really does work as a wireless energy circuit, a commercial driver and a MOSFET with a primary secondary coil and a 50-turn feedback coil. And we have one more circuit to add to our collection. Thank you very much. Now this is one final circuit which could make wireless power, but I'd have to go to a lot of big effort. It's not very easy to do at home. What you do is you have to get a ring of ferrite. I've got a $10 ring, about 60 millimeter. You have to get a bigger ring. And on one side you wrap 12 turns of 1.5 mil copper wire. That's the blue coils. On the other side you wrap about 50 turns. I've labeled the ends in yellows, 12 and 50. And the 12 turns you tap in the middle like that. So you divide them into 6 and 6. And then what you do, you get a DC power supply, and you put 2 diodes on the black and the red just to protect the power supply. The red power plus power comes into the tap part, which is blue, has 6 and 6 on both sides. One wire goes back through the top of the transistor, bottom of the transistor, back to ground. The other wire, the blue wire from the other end of that coil, comes to a 1K resistor into the base of the transistor. Now what happens is, and here's the circuit, plus power tapped in the middle, go both ways. This is the blue coil. One wire goes into the transistor that way, back to ground. The other wire goes into the base. Over here, this is the yellow coil. So interacting with it in a lens sense. Now what happens is when we turn it up to about 10 volts, 5 watts, we get about 110 kilohertz, which is a nice frequency. However, the voltage coming into the second coil is only like 4 times higher than the first coil, so it doesn't go wireless. To go wireless, you need about 500 kilohertz, a much higher frequency, like 5 times, and also you need about a kilovolt at least. So if we wanted to make this circuit work, we would have to get a really big ferrite ring, and we would have to put at least, say, 1,000 turns of copper wire on one side of it. That gets stimulated by this coil here. To confirm, this is the same ferrite coil with primary and secondary coils I just showed you, 12 and 50, and I've tapped into both centers of the coils, the center of the blue coil and the same as the yellow coil. And I've used 2 transistors rather than 1. Now the frequencies are very high, 1600 kilohertz or 1.6 megahertz, which is 16 times higher than before. So that's a really great benefit. This is the circuit we're using, the same as before. I won't get into it. 2 transistors, standard circuit, and we're at 10 volts, which is quite reasonable. So if you want to make wireless energy using this little ferrite device, it's better to use 2 transistors rather than 1 because the frequency is much higher than before. We can also use 2 MOSFETs to make this ferrite ring work instead of 2 transistors or 1 transistor. The key is to fasten the main power supply, DC power supply, to the center of the blue primary coil of 12 turns, which is tapped in the center, rather than the yellow secondary of 50 turns. And we also have to put a 27 ohm resistor in line with the power supply before the primary so it doesn't get blown out. So at 10 volts, 0.15 amps, we get a nice oscillation as seen this cord to a multimeter off 116 kilohertz. So that works quite easily. And this is the same circuit we're using before, except we're tapping here into the blue primary coil, the center, coming off the 2 ends like this. And also we're putting a resistor in here, 27 ohms, right in the power supply there. Now I have also been trying to make wireless energy from 1 transistor and this Flyback Transformer, which I got out of a Samsung TV set. It cost you about $30 on eBay. And it's this standard circuit here called 12 volt Flyback driver, DC power supply, voltage divider, Samsung Flyback Transformer with 10 or 5 turns in the primary feedback coil, and an NPN transistor which has 2 fast diodes to prevent reverse current, and a little capacitor to stabilize it. And there we see the 2 coils, 10 and 5, primary and secondary, which I've just wrapped around. And there are the fast diodes and the capacitor to stabilize the transistor. Now what happens is when we turn this thing on, say to 6 volts, 1.9 amps through it, we only get about 34 kilohertz. So we're getting an oscillation, but it's not enough to make wireless power. Let's just turn it up to 8 volts. 8 volts, 2.2 amps, 33 kilohertz. Now we'll take one end of the secondary coil that's been activated and put it into the other end, and you see an arc.